Some people seem to get really nervous when they're asked about the quotient, product, or power properties. This is an example of the quotient property. The left-hand side shows us expanded form, and the right-hand side shows us simplified form. 6 over 2, or 6 divided by 2, is really our simplified form. But since we can simplify 6 divided by 2, or 6 over 2, further to get 3, our answer could be written as log base 5, 3. So this again was an example of quotient property.
Example 17 is modeled quite similar to example 16. The main difference is that example 17 is illustrating the product property. The left-hand side of the equation shows us expanded form, and the right-hand side of the equation shows us the simplified form. When using the product property, you first identify that the logarithms all have the same base. We also want to make sure that they don't have any coefficients, and if they do, that we put those away as exponents using power property. Last, we just identify all of the logarithmic expressions being added together, find the terms that we're taking the log of, and find their product instead. By looking at the following example, are you able to tell which properties were used to transform the left side to the right side? One of the properties that was used was the power property. The power property is going to allow us to put the coefficient back away as an exponent on the 6. 6 to the second power will then become 36. The sum between the two logarithmic expressions indicates that we need to now use the product property as well. So once we take our log of 6 squared plus log of 1/3, change that 6 squared into a 36, and then finish off by finding the product between the 36 and the 1/3. 1/3 of 36 is 12, so our logarithmic expression will simplify down to log 12 using the power property and product property. For the next example of this type, we're going to start off by addressing the coefficients 5 and 2. Our coefficients indicate that we can simplify the sum of two logarithmic expressions by using the power property. The next line will read log base b of q to the 5th power plus log base b of y to the 2nd power. The sum between two logarithmic expressions indicates that we're going to use the product property to simplify. For the final answer, we will have log base b of the quantity q to the 5th power times y to the 2nd power. This sum of logarithmic expressions can be simplified down to a single logarithm using the power property and product property. I'm going to model rewriting this expression as a single logarithm by first addressing the fact that there is a subtraction sign between two terms and then using quotient property. This will give us log base 3 of 4 over 2, and 4 divided by 2 is 2, so we're left with 4. So we're left with log base 3 of 2. Example 21 also asks us to rewrite the given expression as a single logarithm. I begin this example by first addressing the coefficients and putting them away as exponents using the power property. Next, I address the fact that there's a subtraction sign between the two expressions, which means we're going to use the quotient property to put it into a simplified form. Log of x to the 4th is first and positive. That's going to give me what needs to be in my numerator. Log of x plus 2 to the 6th power has a minus sign in front of it. That means I know which expression needs to go in my denominator. The final answer will be log of x to the 4th over the quantity x plus 2 to the 6th power. The next set of examples are going to work out in the opposite way, where we are given a simplified expression and we are being asked to expand them. Log base 7 of n over 2 being a quotient means we're going to use the quotient property, and we break this down into expanded form, written as log base 7 n minus log base 7 2. The next example has us using product and power property. We do have a product between 11 and p to the third power. First, we're going to separate 11 and p to the third using the product property. We'll have log base 3 of 11 plus log base 3 of p to the third power. If both the 11 and the p were being raised to the third, then we would be dealing with the power property first. Now we can use the power property with the log base 3 of p to the third, which brings us to the next piece, plus 3 log base 3 of p. Example 24 can be solved using a few different options. Option 1 is probably going to be the best bet because it works out the nicest. However, I really do believe that a lot of people are going to try option 2, which does run into a few roadblocks. Option 1, we're going to look at the sum and difference as product and quotient properties. 9 times 36 as our numerator and 4 as our denominator. We're not even going to multiply 9 and 36, but instead we'll reduce the 36 over 4 into a 9. 9 times 9 is 81, and we're left with log base 3, 81, which really asks the question, 3 to what power is 81? You really should know this answer by heart. The solution is 4. Option 2, however, can work in some cases, but in this one, like I mentioned before, we're going to run into a few roadblocks. The first expression, log base 3 of 9, can be figured out. 3 to what power is 9? 2. If you can figure out every single expression, then by all means, do it. However, 3 to what power is 36? 3 to what power is 4? Not so easy anymore. So we wouldn't really follow through with an option 2, but sometimes this can work, so definitely keep your eyes peeled. You really shouldn't need that much support for example 25 because of the practice we've done in the last few examples. We're going to write this as a single logarithm. Single logarithm means 1 log in our final answer, which also means we have to use condensed or simplified form of the 3 logarithmic properties. Here we're going to use product property, and we'll end up multiplying 4 and 3, so log base 5 of 12 is our final answer. For example 26, we're not only going to be expanding this logarithmic expression, but we're also going to simplify it beyond just expanding it. So let's see what we mean. Let's start off by using the quotient property to separate it into log 10 minus log x squared. Let's also take note that we don't have a subscript written. This means the base of our logarithm is 10 because it's common log. If we really have log base 10 of 10, that expression is asking the question, 10 to what power is 10? Since that's something we can do in our head, we should definitely go for it. At the same time, I also use the power property on the second expression to bring the 2 from the x squared as the coefficient of that log x. Since 10 to what power is 10 gives us the answer 1, our final line will read 1 minus 2 log x. Number 27 is the perfect opportunity for a swopportunity. 1 over 16 and 64 really do have something in common. They're both able to be written as 2 to a power. Since 2 to the 4th power is 16, 1 over 16 must be 1 over 2 to the 4th power. 64 can also be rewritten, I know, as 8 squared or 4 to the 3rd, but I always try to go to the smallest number possible, so I'm going to use 2 to the 6th power. That means we'll have 2 to the 6th raised to the 4x minus 3. In the next line, we're going to really use our properties of exponents again to write that 2 to the 4th in a denominator is really the same as 2 to the negative 4th. Then, our 2 to the 6th raised to the 4x minus 3 will follow rules of properties of exponents and multiply the 6 and the 4x minus 3 to get 24x minus 18. Last but not least, we're going to use the one-to-one property. Because we have 2 to a power equals 2 to a power, 1, 2 equals one other 2, where the exponents are written as different expressions, we can set those two expressions equal to each other to solve for the unknown variable x. Negative 4 equals 24x minus 18. Add 18 to both sides. 14 equals 24x. Divide by 24. 14 over 24 reduces by 2, and we get that x equals 7 over 12. Number 28 is another example where we can use the swaportunity and one-to-one property. 16 is going to be rewritten as 2 to the 4th, and 64 will be rewritten as 2 to the 6th. The 4 will be multiplied by the current exponent to create our new power. Once we have 2 to a power equals 2 to a power, we're going to set those two exponents equal to one another and solve for x algebraically. Here we have a classic example of an exponential equation where the swaportunity and one-to-one property method does not work. There's no way to rewrite 36 and 1,500, at least not easily, as a matching base to a power. What we're going to do is we're going to take the natural log of both sides, which is what you'll probably default to more often than not in classes like pre-calculus or calculus. Then what we'll do is utilize the power property and bring the negative 3x out front. All we have to do now is isolate our variables, so we'll divide both sides by negative 3 ln 36. Just be very careful typing this in a calculator, and if you don't have a great scientific calculator, it's probably something you may want to invest in. The other option is to kind of go back to the classic old school way, where we would take log base 36 of both sides. This will end up working out exactly the same as what we did using ln on both sides, except you would just be using the ln in the last step or so when you use the change of base property prior to putting it into the calculator. In this word problem, we can identify that we are given an initial value of 12,000 fish. We also see we have an increase of 4%. 4% for per cent, which means 4 out of 100, and 4 out of 100, 4 divided by 100, 0.04. If we're increasing by that much, we're going to be adding 0.04 to 1 when writing our equation. This question is asking us how many years will it take, so we know we're solving for time, for the population to reach a certain number, so we know that that number, 20,000, is A. If we use the equation A equals P times the quantity 1 plus R raised to the T, we'll fill in everything we just mentioned and have 20,000 equals 12,000 times the quantity of 1 plus 0.04 or 1.04 to the T power. Now we'll go ahead and solve this just like the last example, except this one just happens to be attached to a word problem. We'll divide both sides by 12,000. The zeros will reduce. Then 20 over 12 will even reduce. We get 5 over 3 for that. We'll take the natural log of both sides, bring the t in front, and then divide both sides by the ln of 1.04. Once we punch that into the calculator, we're left with about 13.02438 years.